Hi, this is Kaylee, and let's tackle this inclined Atwood problem, which can be very challenging at times. So, in this situation, there's no friction between the block and the incline, so that simplifies things a little bit. So if we draw a free body diagram of this system, block 2 here, gravity's acting on it, so it has weight, tension from the cords lifting up. For block 1, it also has gravity acting upon it. It has tension, it's going this way, it's going up the incline. And then it has a normal force because it is touching a surface even though there's no friction. So it has a normal force, like so. But when we got anything on an incline, we really need to break up this weight vector into its components parallel and perpendicular to the surface. So if I go over here and resketch that, we have its weight acting down. We have a force perpendicular to the surface. That's symbol for perpendicular. And a force parallel to the surface. That's a symbol for the force parallel. Since there's no friction involved here, I'm not really concerned about the perpendicular part. So I just want to do the force parallel will equal the weight of the object. Now here's the neat thing, because of similar triangles, this angle and that angle are the same thing. So that's 25 degrees. So that's going to be the opposite side. So that's sine of the angle, which will be 25. So that will be mass times gravity times the sine of the angle. In this case, that's m1. We don't know the mass yet. Gravity is 9.8 times the sine of 25 degrees. So if we actually do that, 25 sine times 9.8 gives me, and I'm going to jump back down. I know this is not good math or problem writing because I went sideways then down, but I want to try to fit it all in this one sheet. So the force parallel is 4.14 times whatever that mass is. Okay, we're going to save that. Now we got to figure out this Atwood problem. And the way I do Atwood problems is like this. I usually start off with the force that's causing or affecting the movement is equal to the forces on the system. And the system is the two blocks, earth, everything that's there, the ramp included. And so what's making it move? Well, what's making it move is the weight of this block. So that's M2G, which M2 is 45 kilograms. And then what's holding it back is the weight of this block, or at least the portion of it that's going back down this incline. So we're going to subtract off that force parallel from the first block, and that's got to equal the entire system. The entire system is m1 plus m2 times the acceleration of that system. Now, we want this to stay stationary, right? So if we want this to stay stationary, that means A has got to be 0. So there's no acceleration. So this side falls out, and we get m2g is equal to, when we move this over, the force parallel. In which case, let's see what we got here. We've got m2, which is 45 kilograms. Gravity is 9.8 meters per second squared. Force parallel, we just figured out, is 4.14 times the mass of the first block. So now we can actually solve that. So let's see. 45 times 9.8 divided by 4.14 gives me the mass of block 1 for this whole system to remain sitting still, even though there's no friction, to to be 106.52 kilograms. So that's the balance part. If it's more massive than this, it's going to slide down and cause this whole system to move that direction. If it's less than that, then it doesn't have enough weight to counteract this one, so the whole system will, or this will accelerate up, and the whole system will accelerate clockwise. But that's the balance point. Okay, so we did this one with numbers, basically. What if we don't have any numbers? How can we solve this one just algebraically? So let's try that one. All right, here we've got the same problem, except I don't know either of the masses, and I'm just going to call that theta for right now. We can figure it out later on, but let's just right now just call it theta and not worry about the 25 degrees. So we got the same situation where free body diagram will look nearly exactly the same as the last one, or actually the exact same. Tension the rope. That tension has to be the same. Weight acting down and the normal force. We still, since we got it on an incline, we need to find the force perpendicular and the force parallel. Again, that angle is going to be the same. So if we were actually to break this up, force perpendicular would be the weight times the cosine of the angle. Force parallel will be the weight times the sine of the angle. And again, we don't need to know the perpendicular part, we just need to know the parallel part. So I'm just going to go ahead and shift that into m1g sine of theta. That's the force parallel. If we're doing my Atwood problem, I'll still do the same method. The forces that are affecting movement is equal to the force on the system. What's affecting the motion is the weight of this one and the weight of that one. And the weight of this one parallel to the incline. So we've got m2g, which is the weight of this one, minus the force parallel, which I'm just going to go ahead and write that in m1g sine theta, equals the system, which the system is both masses are going to accelerate together at some acceleration. Now, if we want the system to stay stationary, again, A is got to be equal to 0. So this side falls out. We get m2g equals m1g sine of theta. Well, the neat thing is we've got a g on both sides, so that can cancel out. And I actually want to solve for m1, right? So I want to divide both sides by sine of theta. So now I'm going to move things over. So m1 is equal to m2 divided by the sine of the angle. Now let's check our answer. So we've got one from the previous problem where we actually had numbers. For this one, let's try it. So on this one, let's say that that angle is 25 degrees and m2 is 45 kilograms. Plug them in and we'll see you get the same m1. So m1 equals 45 divided by the sine of 25 degrees. Let's see what we get. So 45 divided by 25 sine equals 106.48 kilograms. And on the previous problem, we had 106.52. And that slight difference is probably due to rounding more than anything else. So for this type situation, our generic equation would be that one right there. If there's no friction, how do these two blocks' masses have to relate to each other in order for the system not to accelerate? Thank you, and tune in again for some more physics. The next one I'll do, we will include friction and see what that does to the problem. So tune in for part 2 of this series. Thank you, and please like and subscribe to the channel. Bye.